Greetings, physics enthusiasts. Welcome to AP Physics 1, Unit 6, Lesson 2. In Unit 6, again, we're talking about waves and wave motion. And last time, I mentioned this SMH, silly, SHM. I hope I wrote SHM and not SMH. SHM stands for simple harmonic motion. And that's what we're going to talk about today, simple harmonic motion. So that was the big secret last time. What does SHM stand for? So something that goes back and forth and back and forth and back and forth could be called, what do we call something that, moves from one side to the other and goes back and forth and back and forth and back and forth and back and forth? Well, that's called an oscillator. And things can oscillate back and forth in a lot of different ways. And so this word harmonic has to do with oscillation. And then we're looking at this simple way. So not everything that goes back and forth and back and forth and back and forth is a simple harmonic oscillator and demonstrates simple harmonic motion. So I'm going to tell you about a very specific way that something can go back and forth and back and forth and back and forth. Then I'll tell you some other things that can go back and forth. And they're still going back and forth, but they're going back and forth in different ways. So here's the thing that I am thinking about that is a simple harmonic oscillator that has simple harmonic motion. Let's say there's a wall and a floor, and attached to the wall, kind of like in the last video, I have a spring, like my slinky last time. I have a spring attached to the wall. Now, springs are as long as they are, but they can also be stretched and made longer. They can also be compressed and made shorter. But their natural length is their length when they are neither stretched nor compressed. They're just lying there. Sometimes that's called L0 for the natural length. And we talked about this last semester when we talked about forces. We said springs will just lie there and be as long as they are. But if we compress them, the farther we compress it, the harder I have to push to keep it compressed that far. And if I want to stretch it, the farther I stretch it, the harder I have to push or pull to keep it stretched that far. But I don't have to exert any force in order for it to maintain its natural length. So what we're going to do is we're going to add a little block of mass M, and we're going to attach it to the end of the spring. And since the spring is neither compressed nor stretched, because the spring's length is its natural length, the spring exerts no forces on the block, and the block exerts no forces on the spring. So if the block is at rest, it will just remain at rest. If the block is moving, that's okay, it can be moving. Right here, it's just going to be moving at constant speed because the spring doesn't push on the block. And there's a special name for this location where the spring does not push or pull on the block. That could be called equilibrium. Equilibrium. I'm not going to say there's no forces on the block because the Earth is pulling the block down and the table is pushing the block up, but the forces on the block add up to zero. So the block is in equilibrium. The block is experiencing no acceleration. Even if it's moving right now, it's not accelerating. So everything's just lying there at rest. Not very exciting, not an oscillator. There's no motion to call simple harmonic. But if I take the block and I pull it to the right, and now I'm holding it here, I'm holding it, nothing's happening. When I let go of the block, the spring pulls the block to the left, and the spring keeps pulling the block, and the spring keeps pulling the block, and the spring keeps pulling the block, and the spring keeps pulling the block. So the block moves to the left, faster, 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 faster. and the block has sped up and gotten here. Since the block is moving, it's going to move beyond equilibrium, but now the spring is going to push the block back this direction, back to the right. So the block's moving to the left, the spring's pushing the block to the right. So the block slows down, slows down, slows down, slows down, slows down, and eventually stops. Well, the spring is still pushing the block to the right, so then the block will speed up and go faster, faster. So the block will go back and forth and back and forth and back and forth. And that is what we call simple harmonic motion. The block is moving back and forth, being pushed on by a spring. So that is SHM, the motion. The block itself is an SHO, a simple harmonic oscillator. The oscillator has the motion. Got it? So we're going to be talking about this throughout the entire chapter in the book, throughout the entire unit 6 here in AP Physics 1. This back and forth motion that we call simple harmonic motion, and this thing that has the motion, which we call an oscillator, specifically a simple harmonic oscillator. So let's look at what caused this motion. What caused this motion was the spring. So do you remember Hooke's law? The name of the law is not important. I'm sure you know this Hooke person was a nice person, but I know nothing about this person except that this equation was named after this person. F, the force exerted by the spring, equals negative kx. Now, so K is called the spring constant. And it's a measure of the stiffness of the spring. This is review. We talked about this back in chapter 4 when we learned about forces. So springs can push things. And some springs are really loose. It's easy to stretch them. They have a small value of K. Some springs are really stiff. I have to push or pull really hard to change the length of the spring. That has a very large value of K. If I were to solve this equation for K, I'd get F over X on the other side. So I can see that the spring constant is force divided by distance. So the unit for the spring constant is newtons per meter. A lot of newtons per meter is a stiff spring. Not so many newtons per meter is a really loosey-goosey spring. The minus sign isn't saying that the forces are negative. What the minus sign is saying is that the direction of X and the direction of the force are opposite. So if X points to the right, F points to the left, and vice versa. They never, X and F never point in the same direction. They always point in opposite directions. So when I displace the block to the right, X is positive. F, the force being exerted on the block, is negative. Okay, positive and negative. When the displacement is to the right, the force exerted on the block is to the left. When the displacement is to the left, the force exerted on the block is to the right. So those directions, the direction of displacement and the direction of the force, opposite. The direction of displacement and the direction of the force, opposite. That's what the minus sign means. Now, so the force the spring exerts is not constant. As I move the block further and further and further to the right, the force exerted by the spring becomes more and more and more. Let's make a graph, because graphing is fun. So if I graph the force exerted by the spring as a function of X, the displacement, and I'm going to graph the absolute value right now because I want my displacement to be positive. I'm going to think about moving the block to the right. Of course, the force exerted is negative, right? But I don't want to graph down here. I want to graph up here. So I just graph the absolute value. When we're here, the force exerted is 0. And then as I go farther, 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 Linearly, I double the displacement, I double the force. I triple the displacement, I triple the force. I quadruple the displacement, I quadruple the force. So I'm going to get a line, and the slope of this line is k. Y equals mx plus b. There's no plus b, so b is 0. That's why my intercept is right here. And the slope is k. Now, you might remember from first semester that when I have a force versus displacement graph, the area here is equal to the work done by the spring. Area equals work done. And we studied that in chapter 5, if you want to go back and review. And of course, this shape is a triangle. And the area of a triangle is 1/2 base height. 1/2, here's the base, x, here's the height, and the height is f, or kx. So if this is x, then this is kx, 1/2 x, kx. Which gives me 1/2 kx squared. That is the work done by the spring. And that should look familiar because we talked about that back in chapter 5. It's the energy stored by the spring. Either way, work done by the spring, stored by the spring. And again, that's review. So let's go back and talk about the spring here. L naught, equilibrium. And now I've got my block that's going to go back and forth. That is simple harmonic motion. It is motion that is caused by a restoring force. This force, this Hooke's law force, is called a restoring force. Now, are there things that go back and forth and back and forth and back and forth that are not governed by a restoring force? Yes. Have you ever, maybe in PE class, sometimes they have you do this exercise where you sprint 10 meters down the field and touch the ground, and then sprint back and touch the ground, and then sprint 10 meters down the field and touch the ground, and sprint back and touch the ground. And you run back and forth and back and forth. You're moving back and forth and back and forth and back and forth. But you're not in simple harmonic motion. You're not being pushed back and forth by a spring. You're running. For the most part, you're going at constant speed and then stopping. And then you're going at constant speed and then stopping. And then you're going at constant speed and stopping. Is that back and forth? Yes. Is that to and fro? Yes. Is it simple harmonic? No, it is not. For something to be simple harmonic motion, it needs to be governed by, caused by, this kind of restoring force where there's something that's pushing harder, 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 and then we stop. And then it pulls less, 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 and then it pulls harder, 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 harder. And then it pulls less, less, less. What if I have a basketball and I drop it? It falls to the ground and then bounces back up, and then falls to the ground and bounces back up, and falls to the ground and bounces back up. Is that going back and forth? Yes. Could I call it an oscillator? Sure. Is it a simple harmonic oscillator? No, it is not. Because all the way down, it's being pulled down with a constant force. And all the way up, it's being pulled down with a constant force. It's not what's going on here. Here in the middle, I'm not being pulled at all. And I'm being pulled harder, 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 less hard, less hard, less hard, less hard. Being pulled harder, 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 less hard, less hard, less hard, less hard. Not the same as a basketball. pulled with a constant force all the way down, pulled with a constant force all the way up. So we have to meet these conditions. It has to be moving like something being pushed by a spring in order to be called a simple harmonic oscillator, and in order for its motion to be simple harmonic motion. So let's look at, we've talked about its displacement. We go from, over here. I'm going to call this negative A, and I'm going to call this A. Ooh, does that remind you at the end last time? Remember in the last video when I showed you a wave like this, and there was an equilibrium, and I called this distance A the amplitude, and I called this distance A the amplitude? Well, in a very similar way, this distance on the right and this distance on the left should be the same. And they're both the number A. This is a distance positive A to the right. This is a distance negative A to the left. So A does stand for amplitude. And do you see that I'm going the fastest here in the middle? Fastest. I'm going to call that the max, the maximum speed. And I might be going really fast to the right. I might be going really fast to the left, but those speeds are the same. What's my speed out here? I could call it V minimum, but of course I stop. So V minimum over here at the amplitude is 0. I also am at that speed V minimum, which equals 0 here. Speed of 0, faster, 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 fastest, slower, 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 stops. Faster, 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 fastest, slower, 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 stops. Make sense? So my velocity has a location where it's going the fastest and 2 locations where it's going the slowest. Let me grab one more color just so I can distinguish the locations in black and the velocities in also black. That's too bad. I hope that would be green. There, now it's green. And now let's look at the acceleration in purple. Black and purple and green, my 3 favorite colors. So where is the, I want you to think about this. At these different locations, basically here and here and here, left, center, and right, where do you think the acceleration is its maximum value? And where do you think the acceleration is 0? So I gave you a little bit of wait time there. If you want to think more, press pause. But here, remember, the spring is not pushing. So if F equals ma, that means A, the acceleration equals F over m. We're going to have more acceleration when we're being pushed harder. And we're going to have 0 acceleration where we're not being pushed at all. The spring pushes the block 0 here. So this is where A equals 0. And way out here, we've got A max. Now, little a for acceleration, big A for amplitude. So that's not confusing, even though they're both A's. This is capital, this is lowercase. So here I have A max, and here I have A max. I have big acceleration because the spring is stretched really far, and therefore the spring is pulling really hard. Over here, the spring is compressed really far, so the spring is pushing or pulling really hard, and therefore I have a lot of acceleration. Isn't that interesting? Where the speed is 0, but I have maximum acceleration. Speed is 0, but maximum acceleration. Here, the acceleration is 0, and I have my maximum velocity. So if I were to make a graph of that, because we love making graphs, if I were to graph the velocity is just down here. Velocity is 0, right? The velocity is 0, and the velocity gets bigger and then less. We increase and then decrease. I start here, I go forward, forward, forward fastest. I'm still going forward, but less, less, less. What about the acceleration in purple, where the acceleration is a maximum? The acceleration is positive here because we're pushing the thing to the right. And then the acceleration decreases to 0. And then the acceleration, since the spring is pushing the block left, the acceleration is negative up to a negative maximum value. So I could just draw a line there, but because of this curviness, maybe I should have a shape kind of like this. And what you might notice at this moment is that this purple graph looks like a cosine. And this green graph is looking like a sine. And we will come back to and look at that more throughout this chapter. But for right now, we're just looking at, hey, I've got an oscillator. It's a simple harmonic oscillator because it's governed by a restoring force. And so what that means is that it starts at a speed of 0 and it goes faster, 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 fastest, slows down, slows down, slows down, stops. And then we continue faster, faster, fastest, slower, 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 stops. So that velocity that we graphed in green would end up continuing that sine curve. And the acceleration would continue this cosine curve. If you're in calculus, you might notice that the derivative of the sine is the cosine. And you might remember that the derivative of velocity is in fact acceleration. If those words did not make any sense, don't worry, you're just not in that math class yet. I promise when you get there, it will make sense. All right. So that is all I wanted you to think about today. As things go back and forth, think about the position here being 0, these positions getting more and more positive, these positions getting more and more negative. And where is the velocity maximum? Where is the acceleration maximum? Notice that those maxima do not occur together. Acceleration max at the ends, velocity max in the middle. And when the velocity is maximum, acceleration is 0. And when the acceleration is maximum, the velocity is 0. Be able to talk your way through that. You should just be able to watch it happen in your mind and then write down what's going on and then make those conclusions. That is simple harmonic motion. Are there other things that go back and forth? Yes. Basketball bounces back and forth. If I'm in a racquetball court and I hit the ball really hard, it goes at a constant speed and then it hits that wall. And then it goes at a constant speed and hits that wall. And then it goes at a constant speed and hits that wall. It's going back and forth, but it is certainly not going back and forth as a simple harmonic oscillator. It is not demonstrating simple harmonic motion. So this kind of thing is. That is all for today. I will see you next time. But until then, have a great day.